Welcome back to Magnetism, Chapter 29. This would be Part 6. And, sorry, this is Chapter 28, Part 6. So, trying to get out of this chapter. That's why I'm thinking about Chapter 29. But every time I try, I think about a couple more things that I want to tell you. And so. Let's get to it. So previously we looked at the problem of shooting a charged particle into a magnetic field, and the problem was even more restrictive than just shooting a particle into a magnetic field. It was where the velocity vector was perpendicular to the magnetic field. So let's just redraw that problem here. So here's a magnetic field into the plane of the paper. We're going to take a charged particle of charge Q, mass M. We're going to shoot it into the magnetic field. The velocity vector is going to be perpendicular to the magnetic field vector. And experimentally, we determined that was a circular path, radius r. And let's look at the quantitative aspects of this. So we go to Newton's second law. F net is equal to object's mass times its acceleration. The only significant force is going to be the magnetic force. The acceleration, by virtue of this charged particle being in circular motion, is radial in nature. And so that's going to be radial or centripetal acceleration. And so we know the radial acceleration is going to be v squared over r, the radius. The magnitude of the force is going to be qvb sine theta. Theta is 90 degrees in this case by virtue of v being perpendicular to b. Sine of theta is 1, so we have qvb is equal to mv squared over r. One of the v's cancel, and we're left with qb is equal to mv over r. In this case, we're going to solve for r. R is now going to be equal to mv over q times b. Okay, and this is going to be the relevant equation for this discussion. And for for you chemists in the room, this scenario was actually the foundation for what is called mass spectrometry. So for some of you who will at some later time either have a research project or when you take instrumental, will actually on the fourth floor go up and use the gas chromatographs that are also connected to a mass spectrometer, so you'll be able to separate your materials by gas chromatography and then determine the molecular mass by mass spectrometry. So what I'm about to lay out here was the original way that it was done, and so let's discuss that in an example. So many of you might have heard about uranium enrichment. This is a topic now that's in the news often when one talks about Iran and their ability to enrich uranium. And so why is that important? Why was it important? Why is it still important? If you were to to mine uranium. Uranium ore in the earth is comprised of two isotopes. So uranium 235 and uranium 238. And the ore is made up of less than 1% of the uranium 235 ore, and obviously greater than 99% of the uranium is in the isotope of uranium 238, right? And recall that these are isotopes. And if you don't recall what isotope is, you should look that up. So the uranium 235 and 238, they differ in some significant properties, right? So uranium 235, we say, is fissile. That is that it's able to undergo fission. The fission process actually means that the nucleus will split up into two daughter nuclides, in that process releasing incredible amounts of power, energy rather, and so uranium 235 was used in one of the two first atomic bombs that were dropped on Japan at the conclusion of World War II. So uranium 238 is not fissile, but it also has some interesting properties. It could be used to make plutonium, which is fissile. So plutonium is fissile, and plutonium was used in the second of the two atomic bombs dropped on Japan. So both of these isotopes were very important during what is called the Manhattan Project. And for those of you who are interested and don't know very much about it, you should give it a whirl and look it up on Wikipedia file. Lots of good chemistry there and physics. But what had to be figured out was a way to enrich uranium 235. So for an atomic weapon, right? Uranium 235 needs to be enriched, because the uranium ore out of the ground is not sufficiently high enough in uranium 235 to actually cause it to be weapons grade. So it needs to be enriched. Typically greater than I think it's greater than 4% or so. Uranium 235 that can be used in a nuclear reactor to generate electricity, and it's going to have to be around 90% or so uranium 235 to be weapons grade. And you could check those percentages. I think I'm probably not too far off. So there had to be a way to enrich those, and there were basically two methods that were established again during the middle of the last century. One was a gaseous diffusion method. Gaseous diffusion method. And one was an electromagnetic method. And so in the gaseous diffusion, uranium was converted to uranium hexafluoride, which is a gas. And then it was sent down literally miles of copper tubing. And the heavier isotope, the U-238 isotope, would diffuse more slowly than the uranium-235, again affecting separation between those two. And so what came out of the tube at the back end was primarily uranium-235 that was enriched. And so the gaseous diffusion method was one method. The other was employing magnetic fields, just like we talked about there. And so let's just highlight that, right? So again, imagine that I form a magnetic field into the plane of the paper, and I have two uranium compounds, actually one compound with two of the isotopes in it. And so what would happen here is you would have uranium-235 hexafluoride, uranium-238 hexafluoride, and you might form the mono cation, right? So ways of stripping off an electron, and then one would shoot those into a magnetic field. And again, there are ways of controlling the velocity, right? We saw that already with the energy selector problem that we looked at a few parts ago. And so you can manage now to get them with velocity which is very much the same for both isotopes. They have the same charge, so Q is the same, but the mass is different. Okay, the magnetic field is constant. And as I said, you can control the magnitude of the velocity. So what happens here, right, is, if you recall then from the equation above, right, R is equal to mv over qb. So R is equal to mv over qb. All of these are constant. So V, Q, and B are the same for each isotope. And so then the radius is going to be directly proportional to the mass. So these would trace out, right? These would trace out two circular paths. One, two. And so out this end, here's radius 1. Here's radius 2. Now the radius is going to be proportional to the mass. So out on this end here, this would be the uranium-238 isotope. This would be the uranium-235 isotope. And basically, although I'm being a little facetious here, right, somebody can just hold a test tube here and collect the uranium-235. Okay, so there's a way of enriching uranium by the electromagnetic method. Both methods were used during the Second World War, during the Manhattan Project, and the history around the electromagnetic method is interesting. the very large mass spectrometer type instruments were called calutrons. And I'll let you look up the origin of that word, which is cool. And the people who ran the calutrons were women, and there was a book written a number of years ago, and it was called the Calutron Girls, which traced the history of both this development of enriching uranium and the very important job that these women had in making enriched uranium. So it's a cool book. You should check it out on Amazon, and maybe while you're in isolation after exams are over, you can perhaps read that book. Anyway, I just wanted to give you this chemical example. Again, the foundations for mass spectrometry. The application of using charged particles through magnetic fields to effect a separation of two isotopes, in this case uranium. And again, there's many other applications of manipulating charges by magnetic fields. And so I'll end this discussion right here, and if you have any questions, please shoot me an email. All right, talk to you guys later. Bye.